Well, I'm gonna get started, even though maybe about half the class is not here yet. So what we'll do today is we'll kind of finish up the top-down design topic by finishing up the last bit of the algorithm. And then we'll also prove a theorem. Okay, so in this class, we'll prove a theorem so that we can use a technique to speed up the process to find a prime factor for a particular number. And I'll pass the test back to you guys. I'm not done grading yet, but I did spend last night like 2 hours to scan all of the exams because it involves de-stapling first, put it through the scanner, putting it back together, restaple, and save the file at the same time. So each one is an individual file in case anyone wants to review your test and you lose yours. I can email you your electronic copy, which can be helpful. So I think this is for this class. Does anyone mind if I just pass it around? Because there are no scores on it, and the first page is really just the name, so there's nothing that has any reflection of your grade of any kind. Is there any objection? Okay, okay, no objections, right? Okay. So if there are no objection, I'll just let you guys pass it around. Just because, I really kind of need to use more lecture time, to talk about the topics instead of using like about 15 minutes, to one, butcher, names of people, and two, to hand it back to everybody. But this way, I kind of miss the opportunity to kind of know, to put a face to a name. In a way, it's a good thing because nobody can blame me and say, but Tag, you're particularly mean with me. Okay, why do you think so? Because, you can see that, my score is lower than other people, even though the answer is about the same. What's your name again? Because if I cannot, put a name to a face, then I cannot, be, doing that. All right, so what we'll do is we'll get started with the topic. And last time, I think we stopped with the overall algorithm. And I mentioned something about, procrastination in this case is a good thing because we are leaving the details of finding a prime factor f of n to be implemented later. In other words, in the main algorithm, the only thing I care about is right here, I need to find a prime factor f of n. I don't know exactly how to do it, I just know what I need to do. Does everybody still kind of vaguely remember that part? Sorry? No? Yes? No? Okay. So I think we did that part last time. Just to be sure, we can take a look at YouTube, just so that we know exactly where we left off last time. And we'll take a look at my channel. Go to my videos, and the class on Monday is this one. Let's just scroll all the way to the end because I don't need to know the rest. Yep, okay, so that's where we left off last time. Let me just make this bigger so that we can see where we left off. Just so that we know. Okay, so this is, let me see, can you do it at a higher resolution? There we go, much better. All right, so this is where we left off last time. We finished the algorithm already, the overall algorithm. The one part that we have not finished, I said, we'll do this. We have to find a prime factor f of n as the first step inside the loop, but I did not tell you guys how to do it. That really is the essence of top-down design. You focus on the big pieces and not worry about the details. And then we specify the details later. Are there any questions about that particular approach? How we ended up with this algorithm? No questions? Okay. So if there are no questions, I just want to bring this up, so that we know the context of, today's lecture. So without any question about that, Now, our main focus now is how do we find a prime factor of a particular number? That becomes the new question. So we'll start with something that's big, okay? Because if I give you a number that is relatively small or easy to spot that it has a particular prime factor, it's not going to be very useful. In other words, if I give you a number that seems to be pretty big, but it ends with a 5, then you can tell me right away, without using any systematic method, you can come back and tell me that 5 is a prime factor. Okay, so it's not going to be very helpful if I want to come up with a very systematic way to find a prime factor of a number. So instead of doing something like this, I'm going to give myself a different type of problem, maybe something like that. Okay, so let's check whether this number is going to be divisible by 3. Nope. Okay, so none of the usual trick that we can use to find a prime factor is going to work on this one. It's not divisible by 2. It's not divisible by 3. Not by 5. So we actually have to work kind of hard to find out whether what is the prime factor of this number. Are there any questions about what I'm about to do? Okay. So what we'll do is we'll use a spreadsheet feature and say that okay, we want to start with 2 as a potential factor, and then we look at the remainder of that number divided by 2. So it becomes mod is the name of the operator. You give it the dividend, which is this number here. So I'll call this $1 to refer to that particular cell. And then 2 is the potential factor here. So we'll put B2 here. You don't have to know how to work with a spreadsheet, but it is useful to kind of understand what a spreadsheet can do. If you want to learn more about spreadsheets, you can take a CISA class, and I think CISA 315 is a spreadsheet class. So if you're kind of interested in okay, what else can I have a spreadsheet to do with for me, you might want to consider taking that class. All right. So 2, if I divide this number by 2, it has a remainder of 1. And let's see. Okay, no luck so far. So we'll go ahead and keep going. Okay, no zeros. No zeros. And it will take, I'm just going to cheat and have it do a whole bunch first. Now we have to spot the 0. Now there's a quick way to spot the 0. Yep. What did I do?
Yeah.
I just drag it down. I selected 2 cells like this. And then I use this little corner here to drag it down. And when I drag it down, it basically replicated the cells that I have selected, and it will just basically replicate. If it's a sequential number, it will just go to the next one, and then the equation on the right hand side, it would actually replicate the equation as well. So that's why it works really well in this case. But I need to look for a 0 in this column, in column C. So let me see if a search can do it here. So let's go ahead and find the 0.
Why don't you just put a filter at the top and then press?
That's a good idea. Can I put a...
Save you some time.
I have to select both columns, right? I might have picked a really big prime number too, just by chance. Okay, so how do I put a filter there? Let's see, filter, auto filter, standard filter, advanced filter. Let's try auto filter. Does not
If you just select the top 2, so the number that you put on there and the one next to it, there you go. And then if you go to the right, you can look for 0.
yeah, it doesn't, there's no 0 yet. Because otherwise a 0 will show up here, right? Okay, that's a good idea. Thank you. All right, so the question is, when can I stop? Let's deal with that one first. Well, okay, maybe not. So I have not found a prime factor yet, so I'm going to keep going and going. This will take a little bit of time. Okay, so go back to the beginning and then say, nope, there's no zero yet. Okay, so, but I think at least it shows the process. You know, it's a very systematic way to try to find a prime factor given a number. I just try the next sequential number. Now, it may not look like the best way to do it because I look at 2, I look at 1. I look at 2, it has a remainder of 1. So why would I even look at 4, you know, and which also has a remainder of 1? Because if 2 is not a factor of this number, 4 cannot possibly be a factor of the same number. Neither can 6, 8, and all the other even numbers. The reason why I keep testing, you know, just a sequential number is it makes the algorithm a lot easier. Okay, because I don't have to skip to just prime numbers. I can just go to the next number, the next number, the next number, the next number. Okay, so keeping this one on screen, okay, I'm going to move this one, scroll it a little bit on the side, so this way it doesn't take up as much space. So this way I have enough room for Notepad, where I will show you how to write the algorithm to do the same thing. Okay. So on this side, inside Notepad, I am going to derive the algorithm. In other words, I'm going to show you, given this is the method that we are trying, I will use a particular method to find out, okay, what is a prime factor of this number. And instead of using this number, let's try something that is easier. Okay, we'll just try 101, which we know is a prime number. And if you look at 101, we won't find a 1, we won't find a 0 until we get to, let's see, we want to deselect all and just select the 0 here. So until we get to 101, we don't find any zeros. Okay, and that makes sense because the one single prime factor of a prime number is itself. In this case, 101 is a prime number, and as a result, it is its own prime factor. Okay, so now we want to. Now, how do I cancel out the filter effect? You can always go to filter and remove it. It's different from Excel, right?
It's different.
Excel is also very useful. There are lots of useful feature in the spreadsheet. So let's go take a look and say, okay, knowing this is the method, how do we write an algorithm so the computer can do it? Okay. So we want to make sure that we know what the algorithm is doing. It's finding a prime factor f of the number n, and n is given to us. All right. So the first revision. Okay, let's start with the first revision here. Does anyone think this particular algorithm or this method of finding a prime factor, is it just sequential or is it repetitive? In other words, am I doing something like, okay, this is how you do it, 1, 2, 3, 4, I'm done? Or is it kind of more of a repetitive nature? Keep doing this until you da-da-da-da. The first or the second? The second. Okay, the second, because it has a repetitive nature, we basically keep doing something until a condition is true. Okay, so just knowing that it has a repetitive nature is already good. Okay, so we will just say that it's some kind of a loop. We don't know what kind of a loop we want to use. In other words, we don't know eventually whether we want to use a post-checking loop or pre-checking loop. But that is not important at this point, because what I want to do is just to identify, is it a loop? Yes, it is. Okay, very good. Do you think this loop will eventually exit? In other words, do we want this loop to eventually exit? Yes. Okay, so we have to specify. Maybe we can just look at the exit condition here and just say loop end loop exit when. When do you think we should exit? Don't worry about using the mod operator and all kinds of stuff like that. Just focus on the objective of the algorithm. When do we get out of this particular loop?
When the remainder is 0.
When the remainder is 0? But more importantly, if you just connect back to the objective of the algorithm, when do we get out of the algorithm? When we find a prime factor. Very good. Okay, so we'll just do that. When a prime factor f is found. Okay, and that's it. That's my first revision. It doesn't look like much, but it tells me two things that are actually quite important. Number one, it is a loop of some kind. Number two, the exit condition involves knowing whether f is a prime factor of n. Okay? So those two things are actually quite important because it gives us a lot of stuff to go on from that point. So in revision 2, I'm going to use your advice and use the remainder method to determine whether f is a prime factor of n, or at least just a factor. Maybe it's not prime. So we'll just say that when the remainder of n divided by f is 0. Okay? Is that a big jump? In other words, if you look at the phrase a prime factor f of n is found, as opposed to the remainder of n divided by f is 0, is that a big jump in terms of concept? I'm hoping it. Sorry?
So it's essentially the same thing.
Essentially the same thing. But it is important because now I'm starting to convert the phrase when a prime factor f of n is found to something that is more programmatic. Okay? Because now we're using operators and comparisons and so on. So in the next revision, I can now actually express the entire thing as an expression. So now we can finally say, hey, there's a way to do this. There's a way to say this in a much more concise way. Is n mod f equal to 0? Great. In other words, instead of using the division symbol between n and f, I'm using the operator called mod, M-O-D, which means we take the remainder of the division, not the usual quotient of the division. Are there any questions about the meaning of the mod operator? Yep.
Can you re-explain it? Sorry.
N mod f gives you the remainder of n divided by f.
Okay.
That's all it does. So you're still you're still performing a division, except I'm not interested in the quotient. I'm only interested in the remainder. Okay. Okay. Let's do an exercise. What is 6 mod 4? Is 2. Okay, very good. What is 15 mod 7? 1. Okay. What is 1 mod 5?
0. Wait.
What is 1 mod 5? What is the remainder of 1 divided by 5?
5.
No.
1. Oh.
What is 1 mod 5? What is the remainder of 1 divided by 5? Okay, I have one piece of candy. Okay, I have one candy. There are 5 kids. I have to spread, candies evenly amongst the kids. Okay, but I cannot chop the candy up because I need whole numbers, right?
Oh, 4.
No.
No.
After I evenly distribute all the candies, how many candies do I have left? That's the remainder. No, 1. Each kid gets 0 candies, and I have 1 left. All right. Okay, let's do a very quick review of division. Okay. Okay, this is the usual way we do division. This part is called the dividend. This part is called a divisor. This part is called a quotient. And this part is the remainder. And I'm pretty sure most people remember, this kind of stuff here with long division, right? Okay. So I can re-express all of these terms, and kind of relate these terms together. So I can basically say dividend equals to divisor times quotient plus remainder. That's how these 4 terms relate to each other. Is that making any sense? No? So when you divide 1 by 5, There's no 5 in 1, so you put a 0 here. 0 times 5 is 0. You have 1 left, but since I'm not interested in the fractional part of this, so it has a remainder of 1. Is that okay? And you can plug this back into here. The dividend in this case is 1. The divisor is 5. The quotient is 0. 5 times 0 is 0. The remainder is 1. So 1 equals eventually 1. It all works out. Okay? Is this part okay? All right. All right, so I'm kind of assuming that revision 3 is okay at this point because all I did was to translate, the phrase when the remainder of n divided by f is 0 to a much more concise form of n mod f equal to 0, which expresses exactly the same condition. It's just spelled out as an expression instead of a phrase. So once we, go ahead.
Oh, when you said 15 divided by 7 or 7 divided by 15? When you said exactly?
I said 15 divided by 7.
And you said it was 1.
The remainder is 1, yes. It has a quotient of 2 and a remainder of 1. All right. Now, revision 3 actually is also very important because if I want this condition to be true eventually, okay, I need to find out what I can change in order to make it true, assuming it's initially not true. Okay? Can I change this 0 to make it true? I cannot. Okay? Doesn't make sense because I do want the remainder to be 0, so I'm not supposed to change that constant. Can I change the problem itself? In other words, you are asking me to find a prime factor of 131, and I'm telling you, you know what? I know 2 has a prime factor of 2. Would that be a good answer? Did I answer your question? No. So I cannot change n, because if I can change n, it's an easy problem to solve, right? So the only thing I can change in this entire comparison is f here. That's the only thing I can change. So that gives me a really good hint of what I need to do in the loop, because I need to change I need to change variable f in the loop so that eventually this condition will be true. Okay. So in the loop, I know that f is being updated. Now I need to look at the spreadsheet, which is immediately to the left-hand side of the algorithm on the screen. So I need to look at the spreadsheet and say, okay, which column do you think is representing f other than the first row? Column B or column C?
I'm sorry, what were you saying?
Which column is representing f? The potential factor.
The second column. C?
Column B. Column B. Column B is representing f. Column C is representing n mod f. Okay? So it's column B. Is there a particular pattern? If you look at each row as one iteration of the loop, how do I get to the next iteration? How do I get to the next value of f?
Plus 1.
Just adding 1 to it. Okay? So that means in the loop here, all I have to do is to keep adding 1 to f and then test the condition. If the condition is not met, go back, add another 1, check the condition. If not met, go back and add another 1. And I will keep doing this until the condition is met, n mod f equals to 0. Is that okay so far? More or less? Okay. There's one more thing that I need to really specify, because I need to know what is the first value that I should try. In other words, how should I initialize f here? What is the first value of f? What is the smallest prime number?
2.
1 is not a prime number by definition.
2.
So the first one would be 2. Okay, so you're both correct. It is 2. So we'll just specify here and say that the first value of f to be tested is 2. In other words, I'm not initializing it to 2 because now we have 2 possible solutions. If I look at revision 6a, which is one particular solution, I can use a pre-checking loop to do it. The pre-checking loop method is to initialize f to 2 and then use a while loop under that. So it becomes while and mod f does not equal to 0, do the following. F gets f plus 1 and while. That's one version of the solution. The other solution is revision 6b. And in revision 6b, we initialize f to 1, but then we use a post-checking loop. When we use a post-checking loop, the action inside the loop is performed at least once, and then we specify and mod f does equal to 0 as the exit condition. So these two loops are equivalent. In other words, solution 6a and solution 6b are identical when it comes to what it's going to do. Which one do you think is better? If you have a choice between these two, which one would you choose? 5? 5 is not a solution. We are comparing between 6a and 6b. Yep.
6A.
6a. Okay, why would you pick 6a instead of 6b?
I don't know, the while loop just seems like it's a better option.
Okay, which one tells you in a much clearer way what is the first value of f to be tested? 6a. 6b is not clear, because if you look at 6b, how do you know that 2 is the first potential factor to be tested? Well, you know because it is first initialized to 1. And then we have to go into the body of the loop, perform f gets f plus 1 exactly once before n mod f equal to 0 is actually tested. So that means f, by the time we get to the test, f would have a value of 2 already. But that's not very clear. It is not really as spelled out as the first one in revision 6a. Because in 6a, we initialize f to 2, and then immediately we have the condition to test. So we know exactly what is the first value that we're going to test. Yep.
And so 6B, although it isn't the better choice, it's still not incorrect?
It is not incorrect. It is just not it's just not a good way of doing it. Because when the algorithm is short, it is still okay, but if the algorithm is longer, it becomes much more difficult to keep track of what is the actual value of f when we perform the test. Yep.
So after we've gone through and we've done this expanding on this, do you move this into the algorithm that we already
That's a very good question.
came up with earlier this week?
That's a very good question. The question was, do we take this solution here, revision 6a, and replace the clause called find prime factor f of n with this chunk of algorithm? At this point, we just basically say, when we see that phrase, we perform this algorithm. When the problem is solved, we go back to the original algorithm to continue execution. But that was a very good question, because we will talk about a mechanism called subroutines in programming
So
that
this
can
would be
accomplish
like
a
this would be like a subroutine then. So it's kind
Exactly.
of like it would be grabbing it from a different place, so you don't
Yep.
necessarily stick it in there. Okay.
Yep. In other words, subroutine is a programming language feature, much like outlining is a feature of a word processor. And the purpose of the feature, or at least one purpose of the feature, is to support top-down design. Just like outlining in a word processor is a feature to support outlining as a technique of writing a paper. That was a very good question. All right, so we are almost done here, except I look at this algorithm and I say, but it's not efficient at all, okay? So it does work, but it's just not efficient. The first thing we'll do is we'll test it, okay? We'll just go ahead and throw some rocks at it and see what happens. So we'll say f gets a value of 2, and because I'm using the Windows version of this, I once again have to go to the options and turn off just about everything. All right, let's do it again. F gets a value of 2, while n mod f does not equal to 0. Do the following. F gets f plus 1, and while. So we'll test this algorithm to see whether it works or not. I'm not going to throw something really big at it, because there's no point in testing it all the way up to 101. So we'll throw something that's relatively quick, so just so that we have an idea of how it works.
I have a question.
Yep,
before you
go ahead.
start. So, just for future knowledge, this is what we're gonna have to make, right?
In the next class, yes. In cisp300, you will be responsible to come up with the algorithm to do it.
Okay, so I was only asking because if we did, I was gonna ask you where you went really quickly to uncheck all that stuff, but I won't need to know.
Oh,
that.
okay. To uncheck all that stuff, you just go to Tools, you go to Autocorrect Options, and go to the Options tab, and uncheck everything except for Use Replacement Table. But in this class, you're not going to write any algorithm, so you don't really have to do that step. In the next class, you'll be writing programs in C++, but then you'll be using a normal text editor to do it. So you don't have to, you're not going to use a spreadsheet to write your program in the next class. All right, so let's go back to, oh, I forgot to open the new window first. There we go. So now we have a new window. And use this one to look at the algorithm, and then use this one to look at the trace. There we go. All right. So let's trace this for like maybe 2 test cases here. We have comments because we have a condition to evaluate on line 2. We have line number, we have 2 variables in this case, although one is really not exactly a variable. I'll just still call it a variable. N has to be given to this algorithm. In other words, the purpose of this algorithm is not to determine the value of n. We start with a value in n first. Our purpose is to find a prime factor for that particular n. So let's go ahead and find something, let's say 15 here. And f is unknown to begin with as our precondition. So let me just shrink the columns a little bit so we can show the entire trace on screen like this. Are there any questions about the precondition? I cannot have n being unknown because I cannot find a prime factor of an unknown number. So n has to start with something. I'm just using 15 as an example in this case. On line 1, f gets initialized to 2. On line 2, we check the condition. N mod f, which is the remainder of n divided by f, in this case is 15 divided by 2, is the remainder of that non-zero. Is it true or false? It is true, okay, because n is 15, n divided by f has a remainder of 1, right? 15 divided by 2 is 7 with a remainder of 1. Is 1 different from 0? It is true. 1 is different from 0. So as a whole, as a condition, it is true. If the condition of a while loop is true, then we have to perform another iteration. So we go to line 3, we add 1 to 2, 2 becomes 3, we go back to line 2. N is still 15, so 15 divided by 3 has a remainder of what? 0. 0 is different from 0 is false. Yeah, that's it. We get the post, we're done. Are there any questions at this point? No questions? Okay. So if there are no questions, what I'll do is I'm going to replicate some of these columns, and then we'll have one more test case, and then we'll move on to the optimization technique here. So in this case, I'm going to erase these lines here and change n to, let's say, a prime number. Let's pick a relatively large prime number, like 17, which is not really too big, but it's still very tedious in this case. This is going to be tedious. You won't like it. If I make this as a homework assignment, you'll say, really, do I have to do I really have to do this? Because it's going to be very repetitive, very long. You kind of know what's going to happen anyway. Okay? But I really want to do it this way, just so that you can see the optimization technique and how well it performs. Okay? Line 1 initializes f to 2. Line 2 evaluates the condition. And mod f is different from 0 is true. Go to line 3, bump f up to 3, go back to line 2. What about this one? 17 divided by 3, does it have a remainder that is non-zero?
Yeah.
Yes, Okay, go back to line 3. Let's check 4. Now I know 4 is not even a prime number, but it's not gonna hurt because 17 divided by 4 has a remainder of non-zero. Okay, in other words, I cannot possibly misidentify 4 as a potential factor. Okay, so we go to 3 again. We now check 5. Go to line 2, and 17 divided by 5 has a non-zero remainder. We go back to line 3. Then we go to line 6. We go to a value of 6. Go back to line 2. I mean, this is not fun, right? I mean, this is boring. Well, that's okay. You know, if it's so boring, we'll do something to kind of speed up the process. Actually, let me think about it. You know what? We'll do this. I'm going to use a feature of a spreadsheet to do it. So from here, I can just copy and paste. And then we can select these, paste it, and then I can now select 4. Oops. Go. Paste it. One more time. And this is one time too many, because these two should not be here. Because by the time f has a value of, oh, I forgot one thing, didn't I? F, there we go. So by the time we get to here, you know, okay, let me show you another technique here. You can show a different row when you split the screen like this. So this way I can still keep track of, you know, which column is what, and still be able to scroll at the bottom part here. At this time, when I get back to line 2, I'm checking n mod f again. This time n is 17, and f is 17 as well. What is the remainder of 17 divided by 17? 0. And 0 is different from 0. It's false. Okay, cool. Now we're done. So it does correctly identify that 17 is a prime factor of 17, except it's kind of tedious. Okay? So what if I tell you that I could have stopped a long time ago? What if I tell you that I could have stopped right here? Right after I tested that 5 is not a prime factor of 17, I could have stopped and made the conclusion that 17 is a prime number. Okay, that would be a good optimization. Okay, it could have saved me quite a few, you know, iterations. The main point of this optimization is we only have to test up to the square root of n to confirm that n itself is a prime number. In other words, if you give me 101 as n, I only have to test up to 11. Not 10, but 11. Because 11 squared is 121, which is more than n already, and I can stop right away and say, oh, okay, 101 is a prime number. Okay? So the question now is, why can I do it like that? Why can I stop, you know, just, you know, at the square root of n, which is the number that I'm supposed to find a prime factor of? Okay, so that has to do with something that we may not have mentioned in this class before. So let me give you a particular statement, and you can tell me whether you think it is true or not. Okay, so here's the statement. So I will just give you, assume n is a positive integer. Assume m is also a positive integer. Okay, and I define product p as nm, or n times m. Let's make it very explicit here. So I have p being, you know, n times m, which is the product of those two numbers. I'm going to bump up the font size just, you know, one size bigger, because I think, you know, it might still be too short, too small for people in the back. Okay, so is that okay so far? I'm restricting, you know, what values n can be. I'm restricting what values m can be, but I'm defining p to be the product of those two numbers. Okay, no big deal here. But one thing I'm going to say is, okay, here's what I'm claiming. TAC claims that this has to be true. Has to be true. Okay, what has to be true is this. What has to be true is p has to be less than n times n, or p has to be less than or equal to, sorry, less than or equal to, not just less than or equal to m times m. Okay? Do you think that's true? In other words, you give me any positive integer, okay, any n and any m. I can tell you that the product is going to be less than or equal to the square of the first number, or the product is less than the square of the second number. Can you prove me wrong?
Yeah, because what if they're the exact same number?
Sorry?
What if they're the exact same?
What if n and m are the same?
Yeah.
Then it will meet both requirements at the same
because
time.
they're equal.
Because of the equal, right? Okay. You can try simple numbers, right? 3 and 5. Okay. If you choose n to be 3, m to be 5, then the product is 15. 15 is less than or equal to 3 times 3 is not true. 15 is less than or equal to 5 times 5 is true. But since it's a disjunction using the or, if one side is true, the entire thing is true. So can you find me a counterexample? I'm not going to waste the rest of the time of today's class to wait for you guys to come up with a counterexample. I'll just say that you probably cannot find one. Okay? But just because you cannot find a counterexample within like 35 minutes doesn't mean that a counterexample does not exist. In other words, just because we cannot find a counterexample to prove it wrong is not enough to prove that it is right either. Is that making any sense? Did I tell you guys about the graduate school story last time? I did? Okay, very good. So I'm not going to say that again. So because it is related to that, okay? Just because we cannot find a counterexample right away doesn't mean it doesn't exist. So what I want to do is to actually mathematically prove that this is the case. Okay? So how do we prove something like this? In mathematics, there's a very powerful technique to prove something. It's called proof by contradiction. Okay, so this is what we'll do. Let's prove this by contradiction. Which is kind of strange, because how can you prove something is right by contradicting it? Well, it's actually contradicting the negation of the theorem itself, not contradicting the theorem that you're trying to prove. Okay? So what we'll do is, when we prove by contradiction, the first thing is to negate the claim itself. Okay? So let's say tech was wrong. Okay? Which happens sometimes. Okay? So if I was wrong in this specific case, then what I'm claiming is no longer true. That means this is not true. Is not true for at least one pair of n and m. You can find me a specific n and a specific m such that disjunction is false. That's what it means when I was wrong in this specific case. Is that making any sense? Because my claim was, if you give me an n that is a positive integer, you give me an m that is a positive integer, and define p to be the product of those two numbers, this has to be true for all pairs of n and m. That was my claim. So when my claim is wrong or incorrect or false, that means you can find me a counterexample, which also means that this is going to be false for at least one pair of n and m. Is that okay so far? Do you guys connect, what it means to be, for my theorem to be wrong to begin with, how to negate it? Okay. So what does it mean when this thing is false? Okay. So let me just go step by step here. So p is less than n times n, or p is less than or equal to m times m is false, is equivalent to the following. Yep.
Is that saying p is less than or equal to n times n? Or just less than?
It's, say again?
Is that stating that p is less than or equal to n times n?
Or
P is less than or equal to M times M?
yep.
Okay.
Yep. But I'm claiming that it is false. Okay. So how do we? What is the other way to say that this is actually false? Well, we can put a negation on both sides. Okay. In other words, what we can do. Okay, this is Boolean algebra, which don't worry, it is not going to be in your test. Come on, multiply. Here we go. Okay, so now we have basically we're stating this, right? The whole thing is false. So if I negate both sides, then one side will be true, and then the other side would be kind of like a big nasty negation thing, right? It's just like in normal arithmetics. If you take a negation of both sides, the equality will still be holding, except you're looking at things from the flip side perspective. Is that okay with you guys? I just took the negation, a logical negation of both sides. Is that okay? All right. So if that is okay, then what does it mean? What is the other way to spell this out? Well, one way to spell it out, I'm not going to prove it here because it's not the right place to do it, not the right class to do it. But this can be expressed as it is not the case that P is less than or equal to N times N, and it is not the case that P is less than or equal to M times M. Okay. Now going from this step here to this step here, this is called DeMorgans Law. DeMorgans Law is kind of funny, right? But it's also useful because it can turn a disjunction into a conjunction. You can see that the negation used to be outside the disjunction. Now it is distributed into the conjunction onto both sides. And you don't have to, you don't have to understand, the DeMorgans Law. We might have other opportunities to apply the DeMorgans Law. You know what? Just because we're here already, I might as well just explain what it is and how to prove that DeMorgans Law actually works. And since I'm writing this on the whiteboard, it's not going to be important, okay? As far as this class is concerned. Yep.
10 minutes.
Thank you. This is the 9 o'clock class. Yep. Okay, so I might as well explain what is DeMorgans Law and how to prove that it actually works. What DeMorgans Law is saying in general is if you have an expression of A or B, and then you take the negation of the entire disjunction, there's another way to say this. The other way to say this is basically just saying not A and not B. Okay, that's my claim. Okay, this is like a mini claim that I'm making, but I need to prove this one first. Okay, does everybody understand what I'm trying to prove here? You look at this expression, and I say that it's the same thing as this expression here. Does it make sense to some of you? To some of you, it might be actually intuitive. Not A or B is to say not A and also not B. Okay, but just because it feels right intuitively doesn't mean that it is also right. So I'm going to prove this one, once and for all, and say that it has to be right. A is a Boolean value, B is a Boolean value, because OR and also AND can only work on Boolean values. And a Boolean value can only be true or false. So A can be true or false. While A is being true, B can be true or false. While A is false, B can also be true or false. We have seen this a few times already. It's called a truth table. So by enumerating all the possible combinations between A and B, now I can look at the results of the two expressions. When A and B are both true, the disjunction itself is true, which means the negation of the disjunction is going to be false. Okay. True or false is true, not true is false. false or true is true, not true is false. This is the only time when it's going to be true, because false or false is false, not false is true. Okay? Is everybody okay with the first column? Okay. So now we will do the same thing with this one here. A is true, not A is false. B is true, not B is false. False and false is false. Second row, A is true, B is false. Not true is false. Not false is true. We have false and true, which is
False.
false. On the third row, we have false, true. A is false, not A is true. B is true, not true is false. Then we have true and false. What is true and false?
True.
False. And the last row, we have false, false. So not false is true, not false is true. What is true and true? True? Okay. Do you see those two columns being identical? Yep. So when you look at this column and you look at this column, they are they have identical values for every single row. That means these two expressions are equivalent as far as Boolean logic is concerned. Is that okay? And this is called DeMorgans Law. DeMorgan is a logician who came up with this particular theorem. All right, so now that we have proven that, we know how to go from this step here, because this is our A and this is actually our B. It's just that it looks a little more nasty. All right, so I'm going to rewrite this a little bit here. What is the other way saying that P is not less than or equal to n times n? How can I get rid of the negation and make it easier to read?
P is greater than?
P is greater than n times n. Okay, very good. So P is greater than n times n. That just sounds a lot better than the other way around. What about this one? Same thing, right? It is not the case that P is less than or equal to n times m. It's just saying P is greater than m times m. Right? Are we still doing okay so far? I just took the negation out by flipping the comparison in the inside so that they mean exactly the same thing. All right. So apparently there's no problem here. What is the big thing? What is the big deal here? Well, the big deal is P is greater than n times n, and P is greater than m times m. And we know that n is positive, m is positive, and p is positive, right? So the whole thing means, if I just multiply everything together, then we have p times p being greater than n times m times m. Is that okay? Or I should say implies in this case. Okay. If p is positive and is greater than n times m, which is also positive, and p is positive, m times m is positive. If I just combine those two and do a multiplication, the equation, the inequality should still hold. Is that making any sense to you? More or less?
Why would you multiply them?
Well, because then I can do something really funny in the next step.
I'm trying to figure out how you went from less than equal to greater than.
It's the negation.
It's the same thing. They mean the same thing, those two lines. The not P is less than or equal to n times n is the same thing as P is greater than n times n.
Yep, so if you look at one single piece, we look at this one piece here, it is not the case that P is less than or equal to n times n. It's really saying the same thing as P is greater than n times n. Is that okay?
Yeah.
Okay. So that's how we can do the conversion. Okay. And the last one is this part here. Okay, I take one P from here and put it here. I take the other P from here and then put it here. I take the n times n from here and then put it here. I take the m times m here and put it here. We know all of these terms are non-negative to begin with. Okay, if some of these can be negative, it doesn't work out. We cannot claim this. But since they're all non-negative, we can actually make this claim. Is that okay so far? Is everyone okay with this line here? That if I know this is true, then I automatically know that this has to be true as well, because they're all non-negative terms. You can look at a few examples. Okay, 3 is greater than 2, 4 is greater than 3. Okay, 4 times 3 is greater than 3 times 2. Is that making sense? Okay, so same thing here. If I make these variables, a is greater than b, and they're both greater than or equal to 0, that's a requirement. C is greater than D, and they're both greater than or equal to 0. Then these two, we can use it to imply A times C has to be greater than B times D. Is that making any sense? Intuitively? Okay, so that's why I can make that claim. Now, once I make that claim, something really, really funny is going to go on in the next stage. What's going to happen next is P times P is one side, we'll just leave it the way it is. But on the other side, I'm going to rearrange things a little bit, okay? What I'll do is I'm going to use the commutative rule of multiplication, because I can change the order inside the multiplication any way I want to and preserve the actual value of the product. So in this case, I'm going to change things a little bit so that I rearrange things to be n times m times n times m. In other words, all I did was to exchange these two guys, the position of these two guys. Is everybody? Yep, go ahead.
Why?
Why?
Yeah, just out of curiosity. I mean, I understand they're the same thing, but
What is
why
the-
are
yep.
you doing that?
Because the next step is also going to be interesting. Because, okay, all right. So let me just kind of put these lined up so that we can see how they compare. Okay. So the next one is, what is the definition of P? If you look up here, what is the definition of P? P is defined to be the product of n and m.
Okay.
Right?
All right.
That's why I rearranged things a little bit, because now I got a interesting thing, because n times m is P, n times m is P. So now I have P times P being greater than P times P. Can that happen?
No.
All right. So that has to be a statement that always has to be false, right? And yet earlier I claimed this expression is true for certain cases of n and m. And that's why we end up with a contradiction. Okay? This is proof by contradiction. By saying that my original theorem was incorrect, I come to a conclusion of something that is impossible, a contradiction. So if it is not possible that my theorem was wrong, what is it really saying? The theorem was right. Okay? And that's a very interesting way to prove something, but it works. It works exceptionally well for a lot of problems. I'll give you another question, another one to use a proof by contradiction. I have, let's say, 2 kinds of socks in my drawer. Okay? Only 2 kinds of socks because I go to Costco, and every time I go, I just buy like a ton of socks. So this way, I don't have to deal with matching socks a whole lot. Okay? So early in the morning, I want to pick a pair of socks to wear to school. The question is, what is the minimum number of socks that I have to, okay, I take it back. What is the maximum number of socks that I have to pull out of my drawer to get 1 pair? 2. No. I have 2 kinds of socks. The maximum number of socks I have to pull out of my drawer to get a pair is 3. If I pull 3 socks out of my drawer, I'm guaranteed that there's a pair.
But you pull 2. Yeah.
Because there are 2 kinds of socks in my drawer.
You get 2 different ones. First 2.
If I get 3, then I have to get at least 2 of the same kind. 1 kind will have exactly 2. Now, is that always the case? Is it possible that sometimes I need to pull 4 socks out of my drawer to get a pair? Well, let's say it is, okay, because I want to prove by contradiction. If I have to pull 4 socks out of my drawer to get a pair, that means the other 2 cannot be the same, right? So now I have 3 kinds of socks, which contradicts my original claim of I only having 2 kinds of socks.
But
So
how many pairs of socks do you have though? Because if you had,
you mean how?
well, I guess it doesn't matter.
It does not matter.
It doesn't matter.
Yeah, because the whole thing is, yeah, I think most of you are getting the idea. Okay, so let's say crosses is one type of socks and circles are the other ones. Okay, so I have all kinds of socks in my drawer, and the number doesn't even have to match. Okay, I can have an odd number of circles and an odd number of crosses because I lose my socks somewhere. Okay, if I just randomly pick 3 out of my drawer, I'm guaranteed to have 1 pair. That's my claim. That's all I'm claiming. Okay. And that can be proved by contradiction as well. And just for fun, and I know this is sometimes politically incorrect, to understand the power of contradiction, you also want to watch the movie called Dogma. Some of you are smiling because you have seen that movie. If you have not seen that movie, just at least watch the beginning part of the movie. If you cannot get past the disclaimer part, don't watch it. Okay? If you can't get past the disclaimer part, it's actually not a very bad movie. Yeah, I will just give you one cast, and that pretty much tells the rest of the whole thing. George Carlin was he Bishop of New York City? Cardinal. Yeah, he was playing Cardinal of New York City. Yeah, that pretty much sets the tone of the entire movie. And there's Silent Bob. What else is?
Jay.
Yep.
Chris Rock.
Chris Rock. Yep, that's right.
And I think Alanis Morissette.
Yeah, she played God.
As God.
Yep. Yep. Well, you're giving away too much.
Sorry.
You're giving away too much. Well, since you're giving away that much, I might as well mention that there's a blessed golf club. There's a golf club that was blessed, not for the purpose of demon slaying, but eventually ended up, being useful for that purpose. Your little puny golf club cannot hurt me. Oh, it's blessed. That was funny. That was a really funny scene. All right. Okay, so we have just gone through the process to prove something is right. Okay, so that means after all this process, we have proven that my original claim, which is this one here, is actually true. Why is it useful in our algorithm?
Wait, we proved that it's true?
We prove that we prove that it cannot be wrong. We prove that it cannot be false, because if it is false, we come to a contradiction, which cannot be the case.
So, what you're trying to say is that when we start out with this whole process, we
Mhm.
set something, we assume that you're wrong. And then when we start with the assumption, we're trying to prove that to be true. If we fail to prove that to be true, then your original claim is true.
Correct. When we try to prove myself wrong, we came to a contradiction. And that's why the original claim has to be true. So we started out with this one, okay? We started out with what I actually want to prove to be true, okay? And then we apply the technique of proof by contradiction. The process of proof by contradiction is to negate the claim first, to say that it is not true for at least one counterexample. Okay, so let's just say that you can find a particular value of n, a particular value of m, such that the original claim was wrong. And I don't even care about the exact value, I just know that it exists. Okay, just the existence of n and m is already suffices. And then from that claim, I proceed to use just Boolean algebra and normal algebra to come to the contradiction. So that means the negated version of my claim cannot be true. But that also means the original version of my claim has to be true, because the negation cannot be true means the original has to be true. So that's how I proved the original claim to be true. But the original claim is valuable to us because what this is telling me is if a number is composite, in other words, if a number is the product of two numbers, then the square of at least one of those numbers has to be greater than or equal to the number itself. And that's why we can stop early. Is that making any sense? If a number is composite, meaning that it is made up of multiple numbers, it's the product of two prime numbers at least. That means at least one of the prime numbers, the square of one of the prime numbers, has to be less than or equal to the number n itself, the number that we're trying to find a prime factor of. So if we cannot find any prime factor that is, and the square of the prime factor is less than or equal to the number itself, then we have just proven that no factor exists. And that's how we can stop short. Okay, let's use a concrete example. Let's go ahead and do a concrete example. Okay. And the concrete example is in the spreadsheet already. This one here. We are trying to look at 101 and say, can we find a prime factor of 101? Okay. So the first thing what we tried was 2 being n in this case. We don't know what m is because with a composite number, the other part is just 101 divided by 2. Okay, but we're trying to see if n is a factor, and it is not. Okay, we try to see if 3 is a potential factor. It's not. 4 is not. 5 is not, and so on. So by the time we know that 11 itself is not a prime factor of 101, we know that it has no prime factor. Because if it had any, we would have found it already.
That's nice.
Yep. It saves us a lot of time, especially the larger the number, the more the saving. Because if you look at a huge number, let's say 1,000,000 something. Okay, let's say we have a prime number that is just a tad over 1,000,000. Okay, that means we only have to try up to 1,000 something, and then we can say that okay, that's a prime number. That's a huge saving. The larger the number, the more saving you're getting, and that optimization is much better than say skipping all the even numbers. Because even if you skip all the even numbers, you're only halving the number of comparisons. But if you go only up to the square root of the number, then the saving is actually much better than that. Okay. So now the question is, how do we incorporate this optimization into the algorithm itself? So what we'll do is we'll look at our favorite solution first. Okay, the other solution we are not as fond of. So we'll look at our favorite solution here and say, but how can we get this optimization into this algorithm? Okay, how do you make a loop exit early? In other words, we know that we have to add another condition here, something to do with f times f, compared to n. Okay, and then we need some kind of operator here. We need another comparison operator here. Okay, because that just seems like what we have to do based on the theorem. So now the question is, what do we do to stay in the loop? How should f times f relate to n for me to stay in the loop? Well, we only got a few choices, right? Comparisons only have a few choices. Less than, equal to, greater than, less than or equal to, greater than or equal to. Those are the only 5 practical,
Less than or equal to?
Less than or equal to. You're pretty close, but I think less than will suffice. Because if it equals to, it would also fail the first condition. If f times f equals to n, that means f is a factor of n, which also means n mod f is going to be 0 also. So you can double ensure, put a less than or equal to is not incorrect, but less than will suffice as well. Okay. The next question now is, what do we do about this question mark here? In other words, now we have 2 comparisons. Each one can contribute a Boolean value, either true or false. So should we use an and here, or should we use an or here to make it more like, okay, wait, hold on a second here. if I want the loop to exit early, do I want it to be true more times, or do I want to make it false more times? I want the loop to exit earlier. And for a while loop to stay in the loop, the condition has to be true. So am I trying to make it become false earlier, or am I trying to make it become true earlier?
False.
False, okay. So between the OR operator and the AND operator, which ones is going to make things false more often? AND, okay? So the AND is the correct choice here. All right. So now we have an algorithm that is optimized, but now we end up with a problem because when it does exit, and n itself is a prime number, f is not really a prime factor of n. So we need to somehow fix that, in case, n itself is a prime number, because in this case, let's say n is 101, we will get out of this one when f becomes 11, and 11 is not a prime factor of 101. So what we need to do is to fix it up with a conditional statement. The conditional statement basically has to say, if we exit early, which means f times f is greater than n, causing us to exit the loop early, then we have to do something, because in that case, we have just found a prime number, and for any type of prime number, the only factor it has, the only prime factor is itself. So we have to kind of fix it up with a conditional statement after the loop. But this is only incurring a very small amount of overhead compared to the amount of work that we have to do without the optimization. Does everybody understand why we need a conditional statement afterwards? Let's do it with and without it. Well, let's go ahead and trace this algorithm, okay? And see what happens when we are dealing with the other trace that we had earlier. Sorry. You were looking at this? Okay. I'm kind of hoping, even though the proof part of this is not required, and I will not task you on proving in this class, I'm hoping that most people see the importance of being rigorous when it comes to mathematically proving something. Because if I just claim it is true, it may not be true, and I put it into the optimization of this code, I can end up misidentifying a number as a prime number when it's not, which is not going to be useful. It's not going to be good. Can we move on? Okay. Right. So let's go ahead and move on, and what we'll do is we'll look at the original algorithm. I'm just going to copy and paste this to a new sheet and then trace the other one again. So I'm going to paste it over here and change this one so that it has the optimization that we were talking about. So we'll say and f times f has to be less than n. And then we'll also add the conditional statement after, which is if f times f is greater than n, then f gets n. And if indentation 5, okay, all right. So this is my new algorithm to trace. And we'll use 17 again for our example, just like before. Okay. And so we'll add a new sheet. And do it over here. This one is going to be a little bit longer because the comments will take up more space, because we do have a longer condition to evaluate in this case. Still have line number, and then we have f and n. And let's say it's 17 to begin with. F is unknown to begin with as our precondition. And we'll make our comments a lot wider, as wide as we can, because it takes up a lot more space this time. There we go. Okay. Line 1 initializes f to 2. Line 2 performs the condition, evaluates the condition. N mod f is different from 0 is true, because it is 1. F is 2, 2 times 2 is 4, 4 is less than 17 is also true, so the entire expression is true. Go to line 3, add 1 to f, f becomes 3, go back to line 2. 17 divided by 3 has a remainder of 2, 2 is different from 0 is true. 3 times 3 is 9, 9 is less than 17 is true. I should say n and not 17, so I'm going to fix this one too. Go to line 3, f gets incremented to 4, go back to line 2. 17 divided by 4 has a remainder of 1, 1 is different from 0 is true. Oops, I keep saying, okay, there we go. F times f is 16, because f is 4. 16 is less than 17, which is n, is also true. We go to line 3, we continue to increment f to 5, go back to line 2. 17 divided by 5 has a remainder of 2. 2 is different from 0 is true. F is 5, 5 times 5 is 25. 25 is less than n, which is 17, is false. So now we have true and false, which is false. So we exit the loop. But this time when we exit the loop, we are not getting to post because we have a conditional statement right next to the loop here, starting on line 5. On line 5, we check the condition. F is 5, 5 times 5 is 25. 25 is greater than n, which is 17, is true. So we have to go to line 6. Line 6 doesn't do a whole lot. It just copies the value of n, which is 17, to f. So f is now 17, reporting back that 17 has a prime factor of 17, which is what we wanted to do. So are there any questions about this? Without the conditional statement from line 5 to line 7, we would have made the incorrect conclusion that 5 is a prime factor of 17. So that's why we need a conditional statement to kind of fix it up. Are there any questions about what we have talked about today? Questions? All right. So that pretty much concludes what we have to do today. We are pretty much done with top-down design, and we are going to move on to arrays concepts next week. And arrays are a completely different, well, it's not completely different, but it is an addition to what we have talked about up to this point. So I would suggest that you guys read ahead of me, at least read a little bit into the array chapters and find out what it is, so that next week we can have a smoother transition into the new topic.
Yeah.
Yep.
Can I see the trace school again?
This one?
Yeah, can I just see that, just the whole thing?
Professor, so I don't understand this one when you post it. So this is this one it's the
Okay,
first.
let me stop the recorder for a second.